Hey, what's going on, guys? CMK here. So the last video I've been introducing you to the CMK Computer. What the heck is that? How it works? And in this video, I already have something to show in regards to the chess program that I'm developing in order to run on this computer. Nothing much so far. I can only print the board array, and I've done the mapping of the encoded pieces to the ASCII characters, which takes I get enormous amount of bytes, to be honest. So probably and most likely in the eventual version, I would be forced just to get rid of the entire print board routine with the corresponding bytes that being occupied to map the piece codes to the ASCII characters, because I'm limited to 512 bytes only. And again, like on the LCD screen here, I'm not gonna be printing the board anyway. So currently I'm just printing this to the serial monitor. That's just me for debugging purposes. So most likely, again, like it would be intended like having the real board with the chess pieces on it, and then just turn it on the CMK computer, like input the move, and it outputs the best move, and you just adjust the board position manually on the physical board. I think that's the way to go, assuming the current display. But again, like as far as I'm developing this, and currently I still have a bit of a space, a bit of a room for that print board function, so that might be on the card set list for the debugging phase, let's say, of this chess program development. So if we have a look at the piece encoding and the board representation, so I'm using the hexadecimal 88 board representation as it's done in Micromax by Miller and by the simplified derivative of my own composition, which is called BMCP, which stands for Bare Minimum Chess Program, which I've been covering on this channel quite a few times earlier. And the piece encoding is just exactly like in the BMCP and in Micromax by Miller. So we have the bit that is worth 8 to represent the white pieces to move, and the bit that is worth 16 to represent the black pieces to move. Otherwise, the piece codes are from 3 to 7. And white pawn and black pawn are considered to be different types of pieces because they're moving to the next direction, to the different directions. Hence, the move offset for black and white pawns would be either added or subtracted. And yeah, taking care of the signed integers is another pain that I have on this project, because CMK Computer operates on unsigned integers, so I'll need to decide whether I'm going to be using the 2's complement to represent negative numbers, or alternatively maybe I would go in for a signed bit plus the magnitude. So I'm more like tending to the second approach, but the first one also has some benefits. So I didn't yet take the final decision how exactly am I going to be dealing with the negative numbers, but for now it's fairly enough just to make sure that the entire board, that the bytes that the board array occupies are being printed properly with a proper offset, like line by line. And also, if I set a certain value into the memory, it would get mapped to the corresponding ASCII character and would be printed by the serial port. And that's exactly the thing. That's the exact highlight I'm going to be demonstrating you in this video. And then I'll quickly walk through the print board function. Well, despite the init board label doesn't do much now, so only the print board is actually on the card. So without further ado, let's actually have a look. So first, I need to assemble the program. So see, like already have tons of labels here, and I would just copy the bytes and go into CMK Computer. So FFFD to load the program bytes via serial port. And again, like as I've been mentioned before, on the real deal, I'm debugging this on the real hardware, but because it's a bit of a pain to shoot that using the real camera. And the picture is really better on this emulator. That's the reason why I'm demonstrating how this works on emulator. But again, like when I develop this, I can show you this. So I have this CMK computer, which is real, say like, and it's based on Arduino Nano, right? So I'm using this thing in order to develop. Just plug it to the USB. It's not seen that nicely. So yeah, USB cable here, and that's the way to develop. All right. So okay, oh, sorry, we didn't yet send, so yeah, I need to send this, and then F to actually load, to run, and here it prints the output. So assuming the two sets of 64 squares for hexadecimal 88 board representation. This is exactly what is intended to be here, and we have zeros. We have here we have the index of 0 is being replaced by this ASCII character of a dot. So what I'm going to be demonstrating now is the following. So let's start by clearing the output. Okay, and if I just run f, it should print it again, which it does. Okay, perfect. It just didn't yet test this in the emulator. That's the reason why I'm testing this now. All right, so now if we, so the board array leaves starting from the hexadecimal 200s, and that's the exact place of where the memory is available after. So let's assume we have 124 bytes or 1K of or YK or 1K of ASCII encoded characters. We put them into the memory. They get translated into the 512 integers, and they do occupy the first half of the memory. So I still have the second half of the memory, which is 512 bytes as well, sharing between the program variables and the stack. So program variables here, the main program variable, the biggest program variable here is the chessboard, right? So the chessboard occupies 128 memory cells, and there would be a couple more memory cells to keep the site to move, I believe, right? What else? Yeah, just the board state variables basically, but the main is the board array, obviously. And currently I don't yet have the routine to initialize that. I've just defined the label. And what am I going to be doing now? So I'm going to be using this exact address just right in the simulator, or emulator, call it however you want. So if I say 0, well, actually, let's start by inspecting that memory location. So 0, 2, 0, 0. So here, so this is the very first index of the board array. So this is kind of like, so if you're thinking about this like from the higher level programming languages perspective, so this is going to be board array indexed by 0, indexed by 1, 2, 3, etc. So here I will now be trying to put some values that do correspond to the encoded pieces, right? So this sort of a pieces here. So let's try this 4 first. So I'll put the pawn, knight, bishop, and rook, and in return I assume to have the corresponding ASCII characters representing these exact pieces. Okay, so 0, 9, 0, C, 0, D, 0, E. Okay, let's go. So in order to write to the memory, I just set up the address, and 0, 9, 0, C, so 0, 9, 0, C, 0, D, and 0, E, 0, D, and 0, E. And it gets stored to the memory once I've entered the 4 bytes. And if I run this program again, F, it now should print the ASCII characters for white pawn, white knight, white bishop, and white rook. So let's see if this is gonna happen. And we have pawn, knight, bishop, and rook. And hold on a sec, is this really what I meant? Okay, pawn, knight, bishop, and rook. So pawn, knight, bishop, yeah, and rook, which is exactly what I've been expecting for. Okay, so now let's try the following bytes. So if I just say 0, 2, 0, 4, and the rest is hold on a sec. So where is, so yeah, so 0F and 0B. And then I just have two zeros. Okay, so 0F and 0B and two zeros after. And if I run again, then here should appear white king and white queen and white king after. I believe that's going to be the case. So F, 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 and yeah, it just starts printing from the new, but from like the new array here. But anyway, we have this queen and king, which is the case, which is good. Okay, so far so good. And now let's say on the next row, so 1, 2, 3, 4, 5, 6, yeah, exactly. Now on the next row, I'm gonna be doing the same but for black pieces. And for black pieces, okay, so the address of the second row is the board address plus decimal 16 or hexadecimal 10. So at this address, so this address should be pointing to the A7 if I did everything properly. So 0210, 0210. And here I want to input these guys. So black pawn, so 12, 14, 15, 16, 12, 14, 15. Oh man, what have I done? Nope. Okay. One more time. So 0210. Just misclick. So 12, 14, 15, and 16. So yeah, now hopefully they got overwritten. Right. So so it should be black pawn, black knight, black bishop, and the black rook. Okay, so let's see if that is the case. Okay, black pawn, black knight, black bishop, and black rook, which is exactly the case. Okay, so now if I say 0204, so plus this 4 bytes, and 17 and 13, so 17, these all numbers are hexadecimal, obviously. 0000 and F, 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 F. So now it should be, yeah, which is the case. So let me just clear the output and print this, execute this program one more time. So the memory is just still there. I'm not doing anything to memory yet. So whatever I've entered to the board array until the computer didn't reset, really, it still holds that whatever we have in the memory. And yeah, so I just wanted to make sure that the encoding of the pieces, it was working properly, and that the mapping of the pieces of the piece codes to ASCII characters works perfectly well. And it seems like it does, right? So now let's have a quick look on how on earth this works in CMK assembly. And yeah, it's really challenging to write this in assembly of my own design, because I really like start every time I try to write something, I feel like very short of instructions. And but anyway, so well, this so here the defines are not the bytes, are just the directives. So it's just the fancy way to use just like in C. So in order to use the constants during the byte definition in the source code, in the source bytes, I just using this defines here. So this piece of code is intended to be used to loop over in order to initialize the board array, and this is going to be probably the topic of the next video. And in order to avoid like executing this bytes, because this is the data, this is not an instruction, this is not the instructions, it's just the data. So I just load in the program counter to go to the address of the init board, and init board is here. So the code starts being executed from here. So I'm resetting the A. Okay, so just to give you a very brief idea of the CPU architecture, because otherwise it's probably not going to be that easy to understand what the heck is going on here. So we go to cmkcomputer.ini file in the source folder. So all you need to know about the CPU, I don't know, maybe I've already been talking about this earlier, maybe not, maybe this was on my Code Games channel, I'm not sure, but anyway. So the emulated CPU, I'm writing instructions for, so I'm writing in assembly, and the assembly gets translated into the machine codes intended to be executed by this CPU, but this imaginary CPU that I've developed. So it has two registers, register A and register B. It has the program counter, or in other words, it's the instruction pointer. So it points to the next instruction to execute in the program. It also has the set pointer and zero flag as the only condition for branching the code, right? So most of the time I'm doing two things. I'm resetting both registers. But another important thing to know that I have two instructions, LDA and STA, and unlike the 6502 assembly and CMK assembly, what they do is the following. So LDA loads the value to the A register from the memory address that is following after the LDA instruction, plus the value of the B register as an offset to that memory address. So if you want to load the data, say from the memory address, like ASCII pieces from, so I want to load this byte. So if I say LDA, then ASCII pieces, and assuming that the value in the B register is equal to 0, I would be loading this byte. If B register is going to be equal to 1, I'm going to be loading this byte. And whatever B register value and whatever value we have in the B register, it would be added as an offset to the address of ASCII pieces, and hence I would be picking the proper the corresponding byte from that address. And in case for STA, so set the value of register A to the memory, the same thing happens there as well. So it would be setting the value to the label followed by the STA plus the offset that is stored in the B registers. If not clear what I've just said, feel free to write the commentaries below this video. I'll try to explain that it's as clear as I can. All right, so yeah, so we can so here nothing special. So LDI stands for loading the immediate data to the A register, so literally resetting the A register, and TAB stands for transfer A register to B register, so literally just resets the B registers as well, or otherwise like just replacing the B register with whatever value that we currently have in the A register, right? And then we're loading the constant of FF to the A register, and this is just the zero, not the zero, it's just the terminating byte, and we are using this to stop the loop over the board itself. So once we encounter the byte that is equal to FF in our print loop, this is going to be clear here. So actually, so we're loading this board start, then every loop we do increment the value in the B register. And one day, when the value in the B register would be 128, it would be pointing to the place in the memory where the value is going to be FF. So I can actually demonstrate you this. So if we have a look at the board and the board, hold on a sec, 0 to 80. So we just inspect the address of so FFFC 0 to 8. Nope. FFFC 0 to 80. So here we have this FF. So once we've encountered this, so after here, we're not printing anything else because the next byte is going to be equal to FF, and we just break out of the program. So that's how it kind of works. And in order to set this FF to this exact memory location, this is what is done here. So I'm initializing, reset an A register is needed in this case only to reset the B register. So the offset is going to be equal to 0. Then we're loading the value of FF, the value that we're supposed to be storing, to the memory. and then STA and the board end. So board end gets replaced with the board end gets replaced with the address corresponding to that label or definition. Yeah, in my case, it's not a label, it's just a definition. So I can, so both the labels and the definitions are getting stored into this well, I call it label hash, basically label dictionary. So board 8 0280, and here we have board 8 0280. So this value replaces in the machine code. So if you inspect this precisely, if you just have a detailed look on how these codes work, then you'll see that after opcode that represents the STA, we then have this value of 0280, right? And assuming that the B register has just been reset, so it's equal to 0, then we're going to be storing the value exactly at this address. So if, say, the B register was the value of 1, 2, 3, or whatever, it would be not at the board end, but at the board end plus 1, 2, 3, and whatever we have, whatever value we have in the B register. So how that's clear. And then, so once we have set this byte into the memory, and again, we can expect this byte in the memory, but just type in the address. That's a FFFC to view the memory, then type in the address we want to inspect the memory at. Then we see this FF is just right over in there. And once we set this, we just made sure that the print loop is not going to stuck in the infinite loop, and it's going to drop as soon as it encounters this FF. Instruction. So what happens next? So next we just, so SBR stands for subroutine. So this is just literally a function call. And by the end of the print board, so print board ends here, print return. So here we just return. And this works just like whatever function calls. So we put the address of the next instruction to execute, literally this one, which in this case byte 0 just terminates the program execution. And we just, well, we print nothing on the LCD screen because we're not asking to print anything. So we just so the cursor is still blinking, so we just did execute, and we are waiting for either to execute again or inspect the memory or whatever. So we just did exit from the program thankfully to this terminating byte. So it stands for no operation in CMK assembly, and also automatically, what it does automatically, it does reset the the program counter. So the next time you call the execute routine in this, like here, it just, so just have a look. So no operation just sets the program counter to 0 and returns. So next time this execute fires, when I use the command FFFF, this function execute, which is flashed into the Arduino memory, it's going to fire. And then the program counter would be pointing to the very first instruction again, to literally to this one here. And hence I can run the same program many times. So that's a bit of a design here, a bit of a design description here. It's probably not how things are done in a normal way, but yeah, I think you forgot CMK again for doing things like this. So anyway, we have this. So print board loop. So we start by resetting the A register and transferring the value of A register, which is 0 to B register. So literally resetting both A register and B register. And yeah, I promised to add very detailed commentaries on what I'm just saying. So you'll be able to calmly read through this after and figure out what's going on here on your own. But for now, I just want to give this a very brief overview. And then we are entering the print loop. So what it does, it loads the byte at board start. So board start is 0x, it's 200 hexadecimal. So board start, this is the 200 hexadecimal, and we have already put some pieces there. Hence, in the output, we do have those pieces, right? But initially, there is nothing really. So anyway. Whatever value we have here is getting loaded into the A register, because that's the nature of this LDA instruction. Okay, where is this LDA instruction? So what it does, LDA instruction, where's the LDA? So it just loads to the A register whatever at the memory address, or it just reads the next word to represent the memory address plus the B register offset. That's pretty much all about it, right? So we do have the value of the, let's say from the high level languages perspective, after this instruction in the A register, we have the value of board indexed by 0, right? And then we're comparing, is this value is FF, and if it is, this means that we have traversed the entire board array, hence we need to return from this subroutine. So we're jumping to print return, program counter gets here, so from here it gets here, here, and it executes return, popping the address from the stack. It then goes back here and already points to this 0 terminating bytes and ends the program. However, before this happens, we need to traverse all the 128 cells of the board array, right? So what happens there? So otherwise, if it's not FF, so we still need to print the entire board array. So we're going further on. So here is the first push command. So push puts the value, like preserves the values of the A and B registers on the stack. So this is needed in order to keep track of whatever we have loaded in the A register, which represents the content of the current board array cell. And the B register holds the offset of how many cells do we need to add to the board start address, which is 200 hexadecimal, in order to print the next cell respectively of what we're trying to print actually. And then here is another push. Well, I'm not sure, maybe I will get rid of this later on, but for now it's just easier for me to do things like this. So I'm kind of like preserving them again, because later on just some branching is happening there, so just to make sure that I don't lose any data. And then once I've pushed to the stack the values of the A and B registers, I'm free to change them however I want, because after I do pop later on, I will restore them back, right? So here I reset the A and B registers by these two lines. Then I'm loading the content of the file count, which is just a counter to count how many files that we iterate over in order to do two things. So in case if the file counter is equal to 8, I just want to print the space, and this space is here. So it splits the board array from the right part of the board, which most likely is going to be used for p-square table, the only p-square table, like for all pieces, just to give the pieces an idea where to get developed, right? And then if it gets to the value, if the file counter gets the value of hexadecimal 10 or decimal 16, that means that we have completed the single line of our board, and we need to print the new line character and go into the next line, print the next line. And in this print space and print new line labels, we do exactly that sort of a logic. So here we're loading the ASCII character of white space to A register and print this to serial port, and don't forget to restore the stack. And in case of the new line, we just reset apart from loading the value of the new line character, hexadecimal 8 or decimal 10, and print this to serial port. And don't forget to pop the stack after, because we do push here, and if here we jump, then we need to pop, because this pop is not going to fire. Otherwise, if we're not jumping anywhere, then we pop here. So this is important to keep your stack being like balanced, because otherwise it's going to end up as a complete disaster basically. So here, part of just printing the new line, we also need to make sure to reset the file count. So I'm loading the instant value of 0 to the A register, and hence at this point we're sure that in the B register we have the value of 0. We just store STA file count stores 0 exactly to the address of the file count variable, which is available here. Right, and why I'm so sure that the B register is equal to 0 at this point, because before calling this print new line, this can be this and this can happen simultaneously. So just one of this scenarios is going to be on the cards. And before this, we did reset the B register with a value of 0 that was set in the A register. So that's the reason why I know that for sure we have 0 in the B register, either when we go to this print space, which we don't care about, or if we go into the print new line. And here we do care about this because we need to reset the file count. So we did handle both the splitting character, the splitting white space to distinguish between the board array and the p-square table scores, positional scores, and also handle the new line. So after so this enable print next is where we jump back from either print space or print new line. So literally continuing resuming the execution of the major loop. And here, what do we do? This is the most essential. So bitwise ending with hexadecimal F or decimal 15, right? Actually strips the byte. It strips. You have the 16th, the byte that is worth 16 here, being the part of the encoded piece. So if we try to initialize A with this value and then transfer it to B and use it as an offset to reference the ASCII characters, then we will run somewhere here. I don't know. So it's not an option really. So we need to make sure that it's no longer than the length of the ASCII pieces, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15. 16 or 15, just no longer than this this kind of array, and hence the piece type is just a matter of the first 3 bits actually. But yeah, we actually do distinguish. It's kind of like from the black pieces, we only use the last 3 bits, and the bit that is worth of 8 in case for black pieces would always be equal to 0, so it doesn't matter really. So for black pieces we just need to strip this bit that is worth 16, hence we bitwise end with 0f, so this one would turn into 0, and whatever we have, all this would be turned into 0, and whatever we have here would remain basically. And here, in order to actually distinguish between the white and black pieces, here a bit that is worth 8, which is still within this first 4 bits, or for the least significant nibble here, it's also kind of being treated as the piece to draw, and as the piece to map to ASCII characters. And hence here, you see we have this starting from here, so this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, and this is the exact value. So 9, then 11, 12. So it's like 9, 10 is skipped. So 11, 12, and so on. So white pieces are used directly in order to kind of like index this ASCII pieces array. While for black pieces, we need to make sure to strip this bit. It's actually, this one actually represents the entire nibble of 0001, but the only bit being set here is the bit that is worth 16, the rightmost in this most significant nibble. So anyway, after this bitwise end in here, we actually do get rid of this. Get rid of this bit, or get rid of this bit. So eventually, black pieces would be 2, 3, 4, 5, 6, 7, and here is exactly what we have. So skip 0, skip 1, then starting from 2, 1, 3, 4, 5. So here we have the black pieces, and then we have the white pieces. And you just don't think that I'm so smart. That's the invention of Harmgerd Müller, has used this in his Micromax chess engine. I've just copy-pasted his code for 5 years and finally realized how this thing works. Okay, so so this is how we map our ASCII character, our piece codes to ASCII characters. So once we did this bitwise end with hexadecimal 0f. We then use this, we then transfer this value to the B register, and from now on the B register contains the exact offset from the start of ASCII pieces array. So from here plus the value that is in B would result in the corresponding offset that would pick up exactly the piece that we want to print that actually corresponds to the piece that is encoded on a chessboard. Oh my god, so I hope you really get what I just said. I swear I understand this, despite the fact I probably can't explain this properly, but yeah, that's one of the not very significant, but those things that I actually really do understand. All right, so and then after this instruction, so loading the value from the ASCII pieces plus the offset that is in B, which is the piece code, but it was ended with this hexadecimal 0f. We already have the ASCII character being loaded into the A register, and then using the serial command, we just do output this character to the screen, and as a result, we see that this ASCII character has been printed to the serial monitor, representing exactly the pieces that we have set into the board array. So I hope that's clear. And then here, and after, don't forget to pop to just balance the stack. And after this increment, assuming that after this pop operation, A register, again, it contains not the ASCII character anymore, but it contains the last piece code that it has fetched from the board array. And the B register contains the offset from the board start label and how many iterations we made so far. So after this pop, the values of the A register and B register has been restored to hold again like this previous value of the piece code and the offset relatively from the board start. And then also we need to not to forget to increment the value in the memory by 1, so we're incrementing the file count by 1 to make sure that all of this tend to distinguish the spaces and new lines when appropriate value for a file count has been reached. So we need to do this as well. And then eventually we're jumping, so this is the conditional unconditional jump, so load program counter to the print loop. So here we just from here, we just drop back here, and we repeat this iteration, repeat this loop for next character until we hit the very last one, so that we have the FF in the A register. And in this case, we just print to the return. We're not trying to print that or something. Just then we go to print return, and then we pop in the previous address of what the instruction to execute next. And so here returning from the subroutine, and the next byte to execute is this one, and this is the no operation, and we terminate the execution call. This is pretty it from my side, guys. So this is how the print routine works. I'm sorry if this looks like or feels like a bit too overwhelming to you. It's really not. So if you want the same thing but a bit easier, you can reference my bare minimum chess program in JavaScript, which relies on exactly the same piece encoding and exactly the same method of printing the board to the console in this case in JavaScript. But it's in JavaScript, hence it's much easier and without all of this nitty-gritty complications related to this particular design of the CPU that I've created to run the chess engine on it. So yeah, the next thing to consider, I need to come up with a routine that would be automatically initializing the board, so I no longer need to do this manually like what I've been demonstrating you, like by manually putting the values to the address to where to like cell by cell to where the board array starts actually. So instead of doing this manually, obviously need to come up with a routine that would be doing this automatically. And that's going to be the topic of the next video. And all this is still just kind of like a piece of cake because, well, for me personally, what I can't wrap my mind around at this point still is the negative numbers. So I'm not sure how exactly, assuming the current assembly, the current instruction set that I have, the current limitations in terms of the memory size, I'm not sure how, assuming all of this sort of a thing, I would be actually proceeding with the positive and negative offsets for to move our pieces, because again, like the pieces would be going both like the positive offset and the negative offset, not only for the pawns but for literally all of the pieces, right? So, and also the scores during the recursive Nigmax call, the scores should be negated depending on the side to move. So the scores should be positive for white and negative for black, so that should be taken into account as well. Okay guys, so this is it from my side. I'm sorry if it was a little bit too overwhelming, but yeah, sorry for that. So hope to see you in the next video in this series, and hopefully we will initialize our board array automatically at that time. So see you in the next video. Until then, and take care.